have been looking at the notion of diagonalizability, and we found that if A is an n by n matrix, then the characteristic polynomial was defined as the determinant of lambda I minus A, and we found that this is a polynomial of degree n, and since we have assumed everything over the field of complex numbers, this can always be factorized as lambda minus lambda 1 into A 1, lambda minus lambda 2 to the power of A 2, and lambda minus lambda k to the power of A k. The lambda 1, lambda 2, lambda k are the distinct roots of the polynomials, and they are the distinct eigenvalues of A. And the A 1, A 2, A k are called the algebraic multiplicities of these eigenvalues lambda 1, lambda 2, lambda k. Then corresponding to these eigenvalues, we define the eigenspace corresponding to lambda j as the null space of A minus lambda j I, and the dimension was found to be always greater than or equal to 1, and this dimension of W j is what we denoted by G j, and this was called the geometric multiplicity of lambda j. What we observed in the last lecture was, so we had the following result in the last lecture, which was this: if the geometric multiplicity of an eigenvalue is equal to its algebraic multiplicity, and this happens for each eigenvalue lambda j. So, it is not that G 1 equal to A 1 or G 2 equal to A 2, for each j, G j must be equal to lambda j. For if G j equal to A j for each eigenvalue lambda j, then A is diagonalizable, and we found that the diagonalizing matrix P was made up of all eigenvectors along its columns. This was our main result, and we got this assuming another result which we said we will prove later, that the eigenvectors corresponding to distinct eigenvalues, the eigenvectors corresponding to distinct eigenvalues are linearly independent. We had not yet proved it. In this lecture, we will eventually get to proving this result. But let us look at some examples again to illustrate what we have got. Let us look at the first example, the same matrices which we looked at in the last lecture also, 1 minus 3 3, minus 2 0 2, 1 minus 1 3. In the last lecture, we found that the characteristic polynomial was lambda minus 4 into lambda minus 2 into lambda plus 2. Consequently, the eigenvalues were lambda 1 equal to 4, lambda 2 equal to 2, and lambda 3 equal to minus 2, and each root occurs only once, and therefore, the algebraic multiplicity is A 1 equal to 1, A 2 equal to 1, A 3 equal to 1. Again, in the last lecture, we found the eigenspace corresponding to lambda 1 was the set of all vectors in C 3, which were of the form x is equal to alpha into 1 0 1, where alpha belongs to C, and W 2 is the set of all vectors in C 3, which were of the form x is equal to beta into 0 1 1, beta belonging to C, and W 3 was found to be the subspace consisting of all those vectors of the form gamma into 1 1 0, gamma belongs to R. Now, in this case we have G 1, which is the dimension of W 1 is 1, because 1 0 1 is a basis for W 1. Similarly, 0 1 1 is a basis for W 2. So, the dimension of W 2 is 1. Similarly, 1 1 0 is a basis for W 3. So, G 3, the dimension of W 3 is 1. So, in this case we find that A 1 is the same as G 1, A 2 is the same as G 2, and A 3 is the same as G 3. So, the algebraic multiplicity is equal to the geometric multiplicity for each eigenvalue. A m equal to G m. The algebraic multiplicity is equal to the geometric multiplicity for each eigenvalue. Hence, A is diagonalizable. Now, observe that any eigenvector of lambda 1 is from W 1. If you take the eigenspace W 1 corresponding to lambda 1, every non-zero vector from this space is an eigenvector. So, any eigenvector of W 1 is of the form alpha 0 alpha, alpha not equal to 0. Similarly, any eigenvector of lambda 2 is of the form 0 beta beta, beta not equal to 0, and any eigenvector of lambda 3 is of the form gamma gamma 0, gamma not equal to 0. Now, if you see these three eigenvectors, this eigenvector corresponding to lambda 1, this eigenvector corresponding to lambda 2, and this eigenvector corresponding to lambda 3. These are eigenvectors corresponding to the distinct eigenvalues lambda 1 and lambda 2 and lambda 3, and we find they are linearly independent. These eigenvectors which correspond to distinct eigenvalues can be easily verified to be linearly independent. We know how to verify something is linearly independent. Only linear combination that gives the 0 vector is the 0 linear combination. So, easily verified to be linear. This is what we had in mind when we said that distinct eigenvectors corresponding to distinct eigenvalues are linearly independent. Now, this is a statement which we have not yet proved. So, we shall embark on proving this fact. So, we shall now look at the process of proving that for A belonging to C n cross n, eigenvectors corresponding to distinct eigenvalues are linearly independent. Now, for this purpose and also for other purposes that we may study or you may study end up in advanced courses in linear algebra, there are several polynomials that play a crucial role in analyzing a matrix. So, the polynomials play a very important role in a matrix. There are several polynomials associated with a given matrix. We have already seen one polynomial, namely the characteristic polynomial. Analogous to that, there are several other polynomials associated with a matrix. So, we look at in general to start with some facts about polynomials. These facts are very important in a complete analysis of the structure of matrices and linear transformations in general. So, we will now consider only polynomials over the complex numbers. So, we always look at a polynomial p lambda, which is of the form a naught plus a 1 lambda plus a r to the lambda to the power of r. We will assume a r not equal to 0. So, that the degree is r. If only the r is only the constant term is there and all other terms are missing, we will call it the constant polynomial. So, we consider in general polynomials of this type, where the coefficients a naught, a 1, a r are all complex numbers. So, we are considering polynomials with complex coefficients. Now, the simplest polynomials are like lambda, lambda squared, lambda cubed, namely the powers of lambda. Now, suppose A is a n by n matrix. We all know that how to define powers of A. We define powers of A recursively as, we define the zeroth power to be the identity matrix, the first power a power 1 to be a squared to be a into a. Now, having defined a power r, we define a power r plus 1 as a into a power r. Okay. Now, we can easily see that if a power r and a power s are two powers of a, they commute with each other. So, easy to see a power r into a power s is a power s into a power r is equal to a power r plus s for any positive integers r and s. So, we first define the power of a, then we define for any given polynomial p lambda equal to a naught plus a 1 lambda plus a r lambda to the power of r, we define p a. Now, we are defining a polynomial of the matrix A as a naught I plus a 1 a plus a 2 a squared plus a r a r. In other words, in the given polynomial, replace each power of lambda by the corresponding power of a. The first term is lambda power 0. So, we replace it by a power 0, which is identity. Subsequently, we have lambda, lambda squared, we replace them by a squared and so on and so forth. So, given any polynomial p with complex coefficients, we associate it with it a polynomial in the matrix A with complex coefficients. This is again a matrix which is complex. Start with the complex matrix, complex coefficients, the sum of all these matrices again a matrix, and again it could be complex. So, given any polynomial with complex coefficients, we can always associate it with it the matrix polynomial P A. Now, we are going to look at some special polynomials. some special polynomials that B will work with corresponding to the matrix A. So, we are given the matrix A. So, we know we can write down the characteristic polynomials and then find out all the distinct eigenvalues. So, let lambda 1, lambda 2, lambda k be the distinct eigenvalues of A. Okay. That means, these are the distinct roots of the characteristic polynomial. Now, consider this polynomial p lambda, which vanishes at all these points lambda 1, lambda 2, lambda k. So, it has a root lambda 1. So, it is lambda minus lambda 1 must be a factor. It vanishes at lambda 2. So, lambda minus lambda 2 is a factor, lambda minus lambda k. So, this is a polynomial of degree n whose roots it is a polynomial of degree k whose roots are lambda 1, lambda 2 and lambda k. So, this is a monic polynomial because the highest power has coefficient 1. This is a monic polynomial of degree k because there are k factors whose roots are the distinct eigenvalues of A. Is the distinct eigenvalues of A. Lambda 1 is a root, lambda 2 is a root, lambda k is a root. Now, what we do is we construct a lower degree polynomial by removing one factor of these k factors one at a time. For example, we now construct p 1 lambda. When I say 1, I mean from p lambda remove the first factor. So, what do you get? We do not get lambda minus lambda 1. So, we get lambda minus lambda 2, lambda minus lambda 3, lambda minus lambda k. To get p 2 lambda, from p lambda we remove the second factor and we look at only lambda minus lambda 1, lambda minus lambda 3 and lambda minus lambda k. And we continue this process to get k polynomials. The kth polynomial we remove the kth factor and retain all the other factors. So, in short form we will write p j lambda is the polynomial obtained from p lambda by removing the jth, that means p lambda by lambda minus lambda j. That factor is cancelled out. We can write this in product notation as r equal to 1 to k, r not equal to j because the jth factor has been removed, lambda minus lambda r. So, you take all factors lambda minus lambda r except the factor lambda minus lambda j, then we get the polynomial p j lambda, and we do this for j equal to 1, 2, 3 and k. So, thus we get k polynomials. So, each of these k polynomials is a monic polynomial of degree k minus 1, because p was of degree k. Now, we removed one factor. So, the degree becomes k minus 1. Now, let us look at this polynomial p j lambda. The p j lambda has factors lambda minus lambda r except lambda j factor. So, if I put r equal to 1, lambda minus lambda 1 is a factor. So, lambda 1 will be a root. Similarly, lambda 2 will be a root, lambda 3 will be a root. So, all these lambdas will be roots except lambda j. So, we have p j lambda r is equal to 0 if r is not equal to j. If r is not equal to j, that factor will appear here and therefore, p j lambda r will become 0. But if r is equal to j, what will happen here? We will have lambda j minus lambda r, none of these factors vanish, and we get r equal to 1 to k, r not equal to j. It is actually p lambda j. So, it is actually p lambda j. Now, we have this polynomial p j which vanishes at all these points except at lambda j, where it takes this value. So, this is what p j lambda j is. So, this is p j lambda r is 0 if r is not equal to 0. So, this is p j lambda j. Now, we normalize these polynomials. Suppose I define L j lambda to be p j lambda by p j lambda r. What is this polynomial? P j lambda is this polynomial except the jth term. P j lambda r is just this polynomial where we evaluate it at the point p j. So, what does this become? We know that this has all the factors. So, let us write it in the factor form. This will just nothing but the polynomial r equal to 1 to k. I have to let us look at this as we will make this we will make this lambda j. Okay. Then this becomes all the factors lambda minus lambda r and all the factors lambda j minus lambda r from these two definitions, except the lambda minus lambda j factor does not appear in the numerator and the lambda j minus lambda j factor do not appear in the denominator. And we find that L j lambda j is p j lambda j by p j lambda j from the definition is 1, and L j lambda r is p j lambda r by p j lambda j, but p j lambda r is 0 if r not equal to j. L j lambda r equal to 0 if r not equal to j. So, in other words, this L j is a polynomial. If you keep moving along the lambda 1, lambda 2, lambda k's, it lights up at lambda j and takes the value 1 and it just dormant at the other lambda j, 0 at lambda 1, 0 at lambda 2, 0 at lambda j minus 1. The moment you hit lambda j, it peaks up to 1, again at lambda j plus 1 it goes to 0, lambda j plus 2 it is 0, lambda k it is 0. So, L j lambda r is equal to 1 if r equal to j, 0 if r not equal to j. So, we have polynomials L j lambda j equal to 1 2 k. So, we have got k polynomials which are such that each polynomial lights up at one particular eigenvalue and dies off at the other eigenvalues. L 1 takes the value 1 at lambda 1 and 0 at all the other lambda j's. L 2 takes the value 1 at lambda 2 and dies off at all this. So, if you just loosely plot, assuming that suppose lambda 1, lambda 2, lambda k were all real numbers, and if we had plotted this L j. So, let us say we are going to plot L j lambda along the y axis, and this is the lambda axis, and then L j lambda will take the value 0 here, 0 here and it will 0 here, except at lambda j it will take the value 1. So, that is what we mean when we say that this lights up at lambda j and just dies off at all other places. It looks like it is like lambda j is a switch for the polynomial lambda j lambda L j lambda. So, we have these polynomials These k polynomials L 1 lambda, L 2 lambda, L k lambda are called the Lagrange interpolation polynomials corresponding to the points lambda 1, lambda 2, lambda k. These are distinct points corresponding to these distinct points lambda 1, lambda 2, lambda k. So, we have these k Lagrange interpolation polynomials. Let us look at some examples. Let us look at this matrix again 1 minus 3 3 minus 2 0 2 1 minus 1 3. Again this is the same matrix which you have seen at the beginning of the class as well as in the previous lectures, and we have found that the characteristic polynomial is lambda minus 4 into lambda minus 2 into lambda plus 2. Now, what are the eigenvalues? The distinct eigenvalues are lambda 1 equal to 4, lambda 2 equal to 2, lambda 3 equal to minus 2. Now, let us construct the Lagrange interpolation polynomials corresponding to these lambda 1, lambda 2, lambda 3. How do I construct the first polynomial? The first polynomial is constructed by writing the terms lambda minus, and we put the value except the first eigenvalue. So, lambda minus 2 into lambda minus 2 and then divide it by evaluating the numerator at the first eigenvalue. So, it will be 4 minus 2 into 4 minus 2, which is lambda minus 2 into lambda plus 2 divided by 2 into 6, which is lambda squared minus 4 by 12. So, that is the first Lagrange polynomial. The second Lagrange polynomial is again you write lambda minus, and then you skip the second eigenvalue and put the remaining two eigenvalues. And then in the denominator write the numerator with the lambda replaced by the second eigenvalue now. Second eigenvalue is 2. So, it is 2 minus 4, 2 minus 2, which is lambda minus 4 into lambda minus 2 divided by minus 8, which can be written as lambda squared, this plus 2, lambda squared minus 2 lambda minus 8 by minus 8. The third Lagrange interpolation polynomial is again you write lambda minus and skip the third eigenvalue. So, you put the first one 4 and 2, and then in the denominator replace the lambda by the third eigenvalue, which is minus 2, which is equal to lambda squared minus 6 lambda plus 8 divided by minus 6 into plus 4, minus 6 into minus 4. So, it is 24. So, whatever the simplification. So, we have got these three Lagrange interpolation polynomials. Let us look at another example. A is 3 minus 1 1 and then minus 1 3 1 0 0 4. This is another example which we have seen in the previous lecture, and we found that the characteristic polynomial is lambda minus 4 the quantity squared into lambda minus 2, and therefore, the eigenvalues were lambda 1 equal to 4 and lambda 2 equal to 2. There are only two distinct eigenvalues now. The eigenvalue 4 repeats twice. So, the distinct eigenvalues are 4 and 2. So, now the construction of the Lagrange polynomials is much easier now. The Lagrange polynomials are now, since there are two distinct eigenvalues, there are going to be two Lagrange interpolation polynomials. How do I get the first one? Now, I have only out of 2 I have to remove one of them. So, I get lambda minus, I should not take the first eigenvalue, I should take the second one, divided by, in the denominator you replace lambda by the first eigenvalue, which is lambda minus 2 by 2. To get the second one, skip the second eigenvalue and write only the factor involved in the first eigenvalue, and in the denominator replace lambda by the second eigenvalue, you get minus lambda minus 4 by 2. So, these are the only two Lagrange interpolation polynomials for this matrix, because there are only two distinct eigenvalues. So, now we have seen that given any k distinct numbers lambda 1, lambda 2, lambda k, in particular given the k distinct eigenvalues of the matrix A, with these we associate the k Lagrange interpolation polynomials L1, L2, Lk. The special properties of these Lagrange interpolation polynomials is the jth polynomial vanishes except at the jth eigenvalue, and at the jth eigenvalue takes the value 1. So, Lj lambda j is 1, Lj lambda r is 0 if r is not equal to j. This is the special property of the Lagrange interpolation polynomials. Now, let us see how we will use these Lagrange interpolation polynomials. Now, suppose we have these polynomials corresponding to the matrix A. We have seen that corresponding to every polynomial in lambda, we have the corresponding polynomial matrix Lj lambda. So, therefore, corresponding to, let us take a general matrix A, C and n, and then lambda 1, lambda 2, lambda k distinct eigenvalues. Now, once I have distinct eigenvalues k of them, we have k Lagrange interpolation polynomials corresponding to the k Lagrange interpolation polynomials what are they? L1 lambda, L2 lambda, etcetera, Lk lambda. We have the corresponding matrices L1a, L2a, etcetera, Lka. We will use these matrices. Now, suppose U is an eigenvector corresponding to eigenvalue lambda j. What does this mean? This means, since it is an eigenvector, that is AU must be equal to lambda j u, and u is not equal to theta n. So, AU equal to lambda j u, that is the eigen equation, and since it is an eigenvector, it must be non-zero. If that is the case, we get multiplying both sides by a, we get a of lambda j u, that is a squared u is lambda j into a u, but a u is lambda j u. So, lambda j squared. So, a u is lambda j u, a squared u is lambda j squared u, and similarly recursively we get for any power r, a power r u is lambda j power r u for every non-negative integer. A cubed u will be lambda j cubed u, a power 25 u will be lambda j to the power of 25 u and so on, and in general a power r u will be equal to lambda j to the power of r u. So, therefore, if u is an eigenvector, then to calculate the power of the matrix A acting on u, all we have to do is take the power of the eigenvalue and multiply it with the vector. Now, this has an additional implication. Suppose now P lambda is equal to A naught plus A 1 lambda plus A r lambda power r is any polynomial with complex coefficients, any polynomial, then we know P A is A naught I plus A 1 A plus A 2 A squared and so on plus A r A power r. This is how we define P A corresponding to any polynomial P lambda, and therefore, what is P A u? P A u is A naught I plus A 1 A plus A 2 A squared and so on plus A r A power r into u. Now, we multiply A naught I times u is u plus A 1 A times u is lambda j u, because u is an eigenvalue, A 2 A squared u is lambda j squared u, we have just now seen that, and so on A r lambda j power r u. We see that this can be written as A naught plus A 1 lambda j plus A 2 lambda j squared plus A r lambda j power r into u, and the what is in bracket is nothing but the polynomial p evaluated at the point lambda j u. So, P A of u is P lambda j of u. So, what is our conclusion? The conclusion is that if lambda j is an eigenvalue of A and u is an eigenvector corresponding to the eigenvalue lambda j, then for any polynomial P lambda, we are assuming everything over complex, for any polynomial P lambda, P A u is equal to P lambda j u. This is a very important identity, because it says the computation over the matrix, calculating the polynomial matrix's action on u is a very simple action. You have to simply calculate the value of the polynomial at the eigenvalue and multiply it with the vector u. So, this is a very nice simple identity regarding eigenvalues, eigenvectors and polynomials. How do we use this? Therefore, now let us look at a matrix A, and then let us say lambda 1, lambda 2, lambda k are the distinct eigenvalues. Of A. Suppose the corresponding, the moment we have the eigenvalues, distinct eigenvalues, we have seen we can construct the corresponding Lagrange interpolation polynomial. Suppose the corresponding Lagrange interpolation polynomials or L1 lambda, L2 lambda, etc., Lk lambda. Then what do we know about them? Remember, Lj lambda r is 0 if r is not equal to j and equal to 1 if r equal to j. This is the characteristic property of the Lagrange interpolation polynomial. The jth polynomial lights up at the jth eigenvalue. Now, we have these k distinct eigenvalues. Suppose phi 1, phi 2, phi k are eigenvectors corresponding to these distinct eigenvalues, or eigenvectors corresponding to the distinct eigenvectors lambda 1, lambda 2, lambda k respectively. So, phi 1 is the eigenvector corresponding to lambda 1, phi 2 is the eigenvector corresponding to lambda 2, and so on. So, what does that mean? A phi j is equal to lambda j phi j for j equal to 1, 2, k, and the phi j are not 0. They are non-zero vectors because they are chosen to be eigenvectors. So, we have A phi j equal to lambda j phi j, and we have just now observed that when you have an eigenvector, the polynomial evaluation is easy. Hence, from our above calculation, P A phi j is equal to P lambda j phi j. This is what we have calculated and found above, that the polynomial matrix evaluation acting on the eigenvector is polynomial evaluation of the eigenvalue multiplying the eigenvalue. Now, how are we going to use it? Now, we were claiming that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So, what we were claiming was that phi 1, phi 2, phi k must be linearly independent. So, let us see how we get it. How do we prove that phi 1, phi 2, phi k are linearly independent? We have to show that if any linear combination is 0, then coefficients must be 0. So, we start with a linear combination. Suppose alpha 1 phi 1 plus alpha 2 phi 2 plus alpha k phi k is equal to theta n. We want to show that alpha 1 must be 0, alpha 2 must be 0, alpha k must be 0. That will establish linear independence. Now, what we do is we multiply both sides by the matrix Lj A, where Lj is the jth Lagrange interpolation polynomial. Now, that will be Lj A into theta n, but any matrix multiplying the 0 vector gives the 0 vector. So, if alpha 1 phi 1, alpha 2 phi 2, alpha n phi n is 0, then Lj A of this must be 0. That says alpha 1 Lj A of phi 1 plus alpha 2 Lj A of phi 2 plus etcetera alpha k Lj A of phi k is 0. Now, phi is an eigenvector, phi 1 is an eigenvector corresponding to lambda 1, and we have seen from this fact that for any polynomial P A phi 1 will be P lambda 1 phi 1. So, Lj A phi 1 will be Lj lambda 1 phi 1. So, this will be Lj lambda 1 phi 1, this will be Lj lambda 2 phi 2, and so on. There will be an alpha k Lj lambda k phi k must be the 0 vector. Now, what is the property of this Lj's? The Lj's are such that they light up only at lambda j, and at lambda 1, lambda 2, lambda j minus 1 they take the value 0. So, therefore, L j lambda 1 will be 0, L j lambda 2 will be 0, and the only term that will survive will be L j lambda j, that term. Because L j lambda j is 1, this will become simply alpha j phi j equal to theta n, because L j lambda r equal to 0, if r not equal to j, L j lambda j is equal to 1. If you use those, you get this. But now, phi j was an eigenvector, and therefore, phi j was a non-zero vector. So, since phi j is a non-zero vector, alpha j phi j equal to theta n implies alpha j equal to. This we can do for every j. If we start with L 1, we get alpha 1 is 0. If we start with L 2 here, we get alpha 2 is 0. So, therefore, for each j equal to 1, 2 up to k. So, that says phi 1, phi 2, phi k are linearly independent, and this is what the result we said in the last lecture that we would prove later. So, the conclusion is that eigenvectors corresponding to distinct eigenvalues are linearly independent. So, this completes our argument that we started in the last lecture about matrices for which the algebraic multiplicity were equal to geometric multiplicity. So, in summary, we have the following result, namely, suppose I have a matrix A which belongs to the complex n by n, and its characteristic polynomial is this lambda minus lambda 1 to the power of a 1, lambda minus lambda k to the power of a k, lambda 1, lambda 2, lambda k distinct eigenvalues a 1, a 2, a k, their algebraic multiplicity. So, we have this eigenvalues and eigenmultiplicity. Then W j, the eigenspace corresponding to lambda j, which is equal to null space of A minus lambda j I, and then we have G j equal to dimension of W j, the geometric multiplicity of A. Suppose G j equal to A j for every eigenvalue lambda j. So, we have, if the matrix A is such that the algebraic multiplicity is equal to the geometric multiplicity for every eigenvalue, then A is diagonalizable. So, how do we then, how to get P such that P inverse A P is a diagonal matrix? In such a case, so in such a case, how do we get the P matrix, so that P inverse A P is a diagonal matrix? What we do is the following: we look at W j has a basis, null space, so subspace, a basis. Now, its dimension is the geometric multiplicity. because the geometric multiplicity is algebraic multiplicity, its dimension is A j, and because its dimension is A j, a basis will consist of A j vectors. As a basis consisting of A j vectors, because G j equal to A j, W j and G j is equal to A j. This is what we are assuming. We are assuming that suppose the geometric multiplicity equal to algebra. So, it has a basis consisting of A j vectors. Let this basis be. So, we always find the null space of, first we find the eigenvalue, then we find the null space, then we find the basis for the null space. Let this basis be phi j 1, phi j 2 and phi j h. And this we can do for j equal to 1 for the eigenvalue lambda 1, j equal to 2 the eigenvalue lambda 2 and so on and so. So, we do this for j equal to 1, 2, 3 up to k. Then construct the matrix P as P equal to, the first you write all the eigenvectors corresponding to the eigenvalue 1. How many of them are there? A 1 of them are there. Write down all the eigenvectors as columns of this matrix P. First look at the eigenvectors corresponding to lambda 1. They come as a basis of W 1. W 1 as a basis consisting of A 1 vectors. Take these A 1 basis vectors and put them as the first A 1 columns of P. This decides the A 1 columns of P. We need totally n columns. Then we write the next A 2 columns, which corresponds to the matrix eigenvalue lambda 2. We continue this process and the last A k columns will be corresponding to the eigenvalue lambda k. So, we will have A 1 plus A 2 plus A k columns, but A 1 plus A 2 plus A k is equal to n. Therefore, we have n columns, and since all the n columns are linearly independent now by the theorem that we have just proved, these are all linearly independent, these are all linearly independent, these are all linearly independent, but across they are linearly independent because we have just now observed that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So, P is a matrix n columns, each column is an eigenvector corresponding to A. The first A 1 columns correspond to the A 1 eigenvectors or the A 1 basis corresponding to W 1. The next A 2 columns correspond to the A 2 eigenvectors corresponding to eigenvalue lambda 2 or same as the A 2 basis vectors for W 2, and continuing this process the last A k columns or the A k eigenvectors corresponding to the eigenvalue lambda k or the same as the A k basis vectors corresponding to the subspace W k, the eigenspace W k. Then since all the columns are linearly independent, P is invertible since columns are linearly independent, and when we write P inverse A P, we get a diagonal matrix. What is this diagonal matrix? The diagonal entries are going to be lambda 1 will appear along the diagonal A 1 times, then lambda 2 will appear A 2 times and so on, and in the end lambda k will appear A k times. So, this will be a huge diagonal matrix, and this is n by n, lambda 1 will appear a 1 times, lambda 2 a 2 times along the diagonal, and finally lambda k a k times, and A becomes diagonalizable. In case all the eigenvalues, if the matrix A is real and all the eigenvalues are real, then P can also be chosen as real if G m equal to A m. So, thus we know that if the geometric multiplicity is equal to the algebraic multiplicity for every eigenvalue, the diagonalization problem can be completely resolved. But the moment we have shortage of eigenvectors, that is, if the geometric multiplicity becomes smaller than the algebraic multiplicity, we have problems. So, whenever G m is equal to A m for every eigenvalue. So, this is the main moral of our discussion. Whenever G m equal to A m for every eigenvalue, no problem about diagonalizability. But unfortunately, it is not always the case. Unfortunately, this does not take place always. That is, there are matrices for which G m will not be equal to A. For example, let us look at a simple example. Consider the matrix A equal to 0, 1, 0, 0. Then the characteristic polynomial, which is the determinant of lambda I minus A, which is the determinant lambda minus 1, 0 lambda, which is thus lambda squared. We have seen this before again. So, there is only one eigenvalue 0 with the algebraic multiplicity as 2. So, let us find the eigenspace. We have to find the null space of A minus lambda 1 I. Lambda 1 is 0, which is the same thing as null space of A. But A is this matrix 0, 1, 0, 0. So, to find the null space, we must solve this equation A x equal to theta 2, which gives us x 2 equal to 0. That is the only equation, and therefore, W 1 consists of all vectors for which x 2 is 0 and x 1 can be anything. And 1, the vector 1 0 is a basis for W 1, and therefore, dimension of W 1 is 1, and therefore, G 1 is equal to 1. So, in this case, we have A 1 equal to 2, G 1 equal to 1, and we have G 1 strictly less than A 1. So, therefore, there are situations where geometric multiplicity is less than algebraic multiplicity, and therefore, we look at a class of matrices for which this is always guaranteed. That is, we would like to have a class of matrix. By looking at them, we can immediately say these matrices are not going to create any problem. For all these matrices, the geometric multiplicity will be equal to the algebraic multiplicity, and these are the so called Hermitian matrices in the complex case and the real symmetric matrices in the real case, and we shall start looking at them in the next lecture.